Yes, good evening, Ahil. Yes, good evening, Ahil. Is my voice audible to you?
Yes, sir.
Okay. So, have you completed the last class homework? Any doubts in that?
Sir, I was gonna complete it today, but then I had just woken up, sir. But because we had mock practicals briefing for the past 2 days, so I was not able to
Okay,
do
so
that.
today was your school.
Uh, no, sir. But I had to prepare
Today
for.
was
No, we
you
had
have to
online,
prepare for that.
online
It was
class.
online.
Yes, we
Okay,
had electrochemistry testing.
schools do still have the online classes going on.
No, sir. It was just like an electrochemistry test.
Okay,
It's not mandatory to do it.
okay.
Also, for current electricity, how many more classes do we have to make?
I think today or not today, so tomorrow. Okay, tomorrow will be the last class of this particular chapter. Which chapter you people want to start after this?
After this, sir, I was thinking wave optics because we had doubts in wave optics.
I think before wave optics, we should do the geometrical optics because once we'll understand the
Okay.
geometrical optics now, and things will become easy for us for the wave optics. Okay,
Yes, sir.
although wave optics is not too much a conceptual chapter, so things will be somewhat there that because what is the problem that people don't used to study the waves in class 11th. Okay, and
Yes.
that sometimes becomes a problem here in the wave optics. So I think that if we study the geometrical optics before the wave optics, so that will be better option for us. Okay, how many chapters are being left first of all
In our school?
for us
No,
uh,
no,
for
for
us to
us.
complete here? Okay, let me see. Let me tell you. Okay,
Yes.
see. Let's first. I think electric charges. You people want to do the starting chapter, starting two chapters as well. Electric charges and field and potential and capacitance. We'll see, or we should see it in the end.
Yes. In the end, sir.
In the end. Yes, Region. What about
Yeah.
you? What do you want?
Uh, Anything is fine with me, sir.
Anything is fine.
Uh,
Okay.
yeah, whichever you think like is better, like I'll just follow that.
See, first of all, we should see for the scoring chapters, and that consists of less time. Okay, so both the
Yeah,
things should be
yeah.
ultimately increasing the uh, gaining of the marks is more important for us rather than completing like the electric charges and fields is one of the chapter. Electrostatic potential and capacitance is one of the chapter that requires a large time. Okay, and as compared to the time that we give and as compared to the marks that we get from it, that is not comparable one. Okay, so that is something. But current electricity was important chapter of moving charges and magnetism. We had completed that, and EMI AC is being completed. Okay, I think magnetism matter. Can we skip that particular chapter?
Yeah, we can skip that. It's all theory, right?
Yes.
So
It's all theory. Okay, so if you people want it, I can take it, but I don't think that we should take it. Okay, last is EM wave. EM wave,
That's
you
also
people want,
theory, right?
that is also a theory one.
Yes.
Okay,
So
in
no worries.
few of the things, just I'll keep on telling you that whenever the question comes this, you have to find out the answer like this. Whenever the question comes like this, you have to find out the answer like this. So but ultimately, it will be the thing that I'll keep on telling you the things, and you'll keep on grabbing the things. There is no conceptual things in that particular thing. Okay, so this was all
Yeah.
about the first book. In the first book, I think we can. do max to max one chapter more. What I think
We're
only two is left now. Hmm?
we're talking about pre-board, right? Pre-board exam. Yeah.
We are talking about the total syllabus.
Oh no, no,
Okay,
I'm saying
so
like what I'm saying is like what all can we like finish till like pre-board? So
in the pre-board, complete syllabus is going to come now.
yeah, but like we won't be able to like like finish everything, right?
Do the
So
complete one. Yes. Okay, so the first two chapters are being actually we can see that that is left in the first book, and in the second book, ray optics, wave optics, and this semiconductor physics is being left. Semiconductor physics consists of all the chapters: dual nature, radiation matter, atoms, nucleus, and semiconductor itself. Okay, so all these chapters are actually a part of the thing that we can complete in the fewer classes. So I think the two major chapters that are being left is ray optics, wave optics, and the two of the previous books. Four and few of the chapters in these books are still will be left. So I think that ray optics we should start in the next class. That is also coming in your pre-boards now.
yes,
Yes.
Okay, so I think we should start the ray optics, and it also consists a very good part, and it is a totally a conceptual chapter, right? Just like this current electricity is going on over here. Okay, so I think we should start the ray optics. We'll start it tomorrow or the class after the tomorrow. Tomorrow will not take more classes over the current electricity after tomorrow. Tomorrow will be the end of it. Okay, so this is one of the things that we had seen, and let's start our class. Okay, let me open the screen. Yes, what were we doing in the last class? First of all,
the
can you people open the camera?
Yes, sir.
right.
So just give me 1 second.
Okay, let's see that first of all, a little recap about the previous class. We had actually had seen done some of the questions over the Kirchhoff's law and had started the terminal potential. I had started the internal resistance of the battery. Yes or no?
Yeah, and practical voltage as well.
Yes, practical voltage. And so actually the internal resistance we had started. Okay. Sorry. Again, let's start with the same question. What is the work of a battery? A 5 volt, let's say. What it used to do?
To establish a potential difference of 5 volt.
Across to whatever
The
the point these two potential are being connected. Okay, so
correct.
does it guarantee anything about the current?
No,
No. Okay, so it does not guarantee anything about the current. Okay, what is actually the replacement of this? Is there anything that through which we can replace this 5 volt battery?
well,
Have I told you anything else also about the 5 volt battery that it used to establish, of course, a potential difference of 5 volt that we can guarantee? And what else it used to do? It is a source of it is a source of infinite charge. It's a source of
okay.
infinite charge. Okay, so if it's a source of infinite charge, so it means that we can actually replace this particular from where we can actually get the charge. If we want some charge, who can give us the charge?
Current
The capacitors.
capacitor.
The capacitors are the one who can provide us the charges. So if we use a very big capacitor, so it will have the infinite charge contained in it. Okay, so
Okay, sir.
we can replace the battery from equivalently. We want the equivalent replacement of the battery. So if we ever want the equivalent replacement of this battery, we can replace it with this. Is this clear to
Yeah,
you?
yeah,
Okay,
sir.
but ultimately, uh, defining anything is the infinite is not a way. Okay, so we never used to say that, of course, it is a source of infinite charge. We always used to say that it establishes a potential difference of 5 volt across whatever the point it is being connected. Okay, it doesn't care
Yeah.
about that what is happening in the world. We don't know about it, and we don't even care. Okay, the
Mm.
only thing that we are always sure about, that it will establish a potential difference of 5 volt to across whatever these 2 points will get connected. This was the story about a ideal battery. Yes.
Yes, sir.
Yes or no? So this
Yes,
was
sir.
actually the story about the ideal battery. Let the hill join fast so that. Okay, so uh, we were talking about that what a battery used to do. Battery used to do that, it used to establish a potential difference of, let's say here we had given the 5 volt, so it used to establish a potential difference of 5 volt across whatever the terminal it is being connected. Okay, it was the something like this. In the last class, we had also seen that if we don't talk about the ideal battery, if we talk about the practical voltage source or the practical battery, okay, we talk about practical voltage source. In the practical voltage source, we had seen that it always comes with a internal resistance, that is small r we used to say, and this is the V. Okay, and instead of V, we used to say it as EMF E. Yes or no?
Yes, sir.
We used to say it as EMF E. Okay, and what is actually given to us? This is actually packed in a particular box. Okay, we can't remove this R anyhow. Okay, it's not in our
Yeah.
control that we can remove this. It always comes inbuilt with the source. We cannot change it. We have the access to these two terminals always. Okay, so this is something that we should know about. Okay, so and this is how we had also seen that its terminal voltage used to get reduced one. Okay, so if we talk about the ideal one, okay, let me, no, control C, let me replace it over here. This is the practical voltage source, and if we talk about the ideal voltage source, ideal voltage source. So what it is, there is no battery being given to us. It is the V actually, let me mark it as EMFE, and there is no internal resistance. Okay. Now, one more thing that I want to say over here is that if it transports a current I, okay, it is connected with somewhere with the external circuit that right now we don't know about. Something is being connected this side, something is being connected this side. Okay. So not need to worry about that. Something is being connected. That is why it is transporting a current I, and it is also transporting a current I. Okay. Now there are the two things. One is called the terminal potential. Okay, so this is actually the terminal potential, the potential drop across these two terminals. The potential drop across these two terminal is actually called the potential terminal potential. If I mark this point as A, mark this point as B, so of course VA minus VB, VA minus VB will be termed as V. Is this clear to you people?
Yes, sir.
And if we talk the same thing in the ideal battery, it is A point over here, B point over here, and this is something E here. If I talk about the terminal potential here, so what will I get? This is the terminal potential V. So what I can see over here, that V is actually equal to E, EMF E. Yes or no?
Yeah. Yes, sir.
V is actually EMF equals to E. Now let us see that what is the if we draw the graph. What I mean here is that if we draw the graph, that if there is this graph and there is this graph that we are talking about right now, and this graph is between the current I and the potential difference V. Okay, before drawing the graph, first of all, let's find out a relation between this. In this LHS circuit, this circuit, if we apply Ohm's law, Kirchhoff's law, starting from point A. Okay, starting from point A and we'll reach to the point B. Okay, so what will be the thing that VA this time plus of I into R? Yes or no?
Yes.
Yes.
Plus of I into R and then
Plus E. And I mean
plus
minus
of
E.
E
Minus.
minus E
Minus E.
minus E and we'll reach to the point B. Yes or no?
Yes.
And if we'll transport the things properly, what we'll get? That VA minus VB is actually equal to E minus of I into R. Yes or no? E minus ka
Sir.
into R. Okay, so can we see that what this VA minus VB is? VA minus VB is the terminal potential that we are treating over here. VA minus VB is the terminal potential. That is the potential that will supply anytime if I connect it with any other any circuit. Okay, and uh, I think for proper thing I should connect it with a resistance R so that things should become clear for you people. Okay, otherwise doubt can be anytime asked that how is the current passing through it. So let me connect it with R. So I think that there will be no change in these equation even if I connect it with R. Okay, still I'm assuming this I current only. Okay, so there will be no issues. Yes or no?
Yes.
Okay, now if I see VE minus of I into R. Now I'm plotting the curve between V and I, V versus I. Yes or no? The terminal potential and the current I. Yes or no?
Yes.
So what the graph should look like here in this side?
Um,
First of all, tell me that is the slope positive or the negative over here in this particular circuit?
Negative slope.
Okay, so what we can see over here that y equals to this E is somewhat constant, C plus of mx. Let me write it as plus of m. Have I done any mistake? Yes, a kind of. Okay, so this V is over x. Okay, so if I want to write it properly, what else I can do? I can actually transport this on the another side. IR equals to E minus V, and if I divide it with R, what I'll get? I equals to E by R minus of V by R. This is a small r. Yes or no?
Yes, sir.
Okay, this I is over the y-axis and this V is over the x-axis. So let me write it as mx plus c. What this m will become here? What this m will be equal to?
E by R.
M. M is something which is multiplied with the x. This is x.
Oh, yes,
This
sir. So
V
E
is
by
x,
R.
na?
Yeah, E
This
by R.
V is x. So M is
Yes,
actually
sir.
minus of 1 by R.
Minus 1 by R.
So slope is negative. And what is the y-intercept that is C?
That is E by R.
That is E by R. Okay, so if we'll draw the curve, we'll get the curve somewhat like this. Okay, we'll get the curve somewhat like this. What this y-intercept will be? See, value of y-intercept will be positive. This is somewhat positive because E is positive, internal resistance is positive. So we can see that this curve is somewhat positive and this is E by R. And what this value V is actually, what is this value? When you will keep I to be 0,
Yes.
when you will keep I to be 0. If you will keep
By
I to be
potential.
0, what we'll get? V to be equal to EMF E. Is this clear to you?
Yes, sir.
So I think this also explains us about the thing that we were discussing in the last class, that whenever the current passing through, what was the case there? That if we talk about this thing, whenever it was in an open circuit configuration, that was the current passing through it was 0 ampere. So the potential drop we were getting has to be same as E. The terminal potential was becoming same as E. Yes or
Yes.
no? Were
Yes,
we seeing the same thing in the last class that if no current is passing through the battery, then the terminal potential becomes itself E. So we can analyze the same thing over here as well. If no current is passing, that is the current should be zero. So corresponding to the zero current, the terminal potential, the point on the x-axis we are getting has to be E. Yes or no?
Yes.
So we can see this, the same thing that we were discussing in the last class also, that if there is no current passing through it, so we'll get the terminal potential to be this. Okay, now the same, if we see the same thing over here in the RHS side, what we'll see that the V is actually equal to E, because E itself is connected across the two terminals A and B. Yes or no? So what we can see that V is equals to E. Okay, so what I can say over here that V and I, if I plot the curve between V and I, so can you see that it is a curve like x equals to constant C?
yes.
Yeah.
Can you see this, that it is a curve like x equals to
Hmm.
constant? So plot this curve, how it will look like.
Just straight up, no.
Yes,
Yeah.
It will
So
just be straight
it will
up.
be a linear curve.
Yeah, like
Just
of
straight
course,
up.
the LHS part is also a linear one. है ना? So
yes.
what will be the special about this in this curve?
So y-intercept will be 0.
Y-intercept will be
0.
0.
It'll start from 0. It's
It will start from 0 and will go like this.
Hmm.
Okay, tell me here,
Mhm.
don't you think that here, whatever the Y you choose, it doesn't matter. You will always get the X to be equal to C.
Yes.
Yes or no?
Yes.
In this curve, what is going to happen? That
So
if
sir,
we
is it a
move to
straight line?
the class 10th discussion, whatever the X and Y, whatever the Y you are choosing, it doesn't matter. You will always get the X to be equal to C.
So is it a straight line, sir?
See the straight line, this is also a straight line, na?
No, as in like vertically a straight line. Same x value for all
Yes,
y
that will
values.
be a vertically straight line, somewhat like this. And even it can go downward as well. Even it can go downward as well. So what do I mean from this? See, if I choose I to be 0, then also I'll get the x to be v. If I choose I to be some random value, I'll get the x to be v only. If I choose some negative value of I, I'll get the x to be v only. This part only. Is this clear to you people?
Yes.
Sir,
So this point will be marked as E. So this is the difference between the do for the ideal source and the practical source. And what we can see over here now in terms of physics, this was in terms of mathematics, that whatever the y we choose, we get the x to be c. In terms of physics, whatever the current is passing through the battery, it doesn't matter. It will always establish the potential difference of E across the 2 points, wherever these batteries being connected. This was the ideal battery that I was repeating from, I think, the second or third class from the very starting. Okay, so in terms of physics, what I
yes,
can say that whatever the current is passing, it doesn't matter actually. Okay, is this clear to you people?
yes, sir.
So this is something that you should know about. Okay, a few things that is something that you should know about. Okay, so let me write it over here. That one is open circuit. Open circuit is something. What is the condition for the open circuit? Whenever is, let's say now we are talking about the practical voltage sources. So let's say that it is a, also one thing also you should know about, that whenever we are talking about the internal resistance, it could be drawn behind this battery as well. Okay, so not need to necessary that it will always get drawn like this only. It can be drawn in any way. Okay, so if this is the battery like this, and I had not connected with any source, I had not connected it with any source. So what are we always sure about?
No flow of current.
Yes, no flow of current. So in open circuit, I will always be zero.
Oh yeah.
And what will be the V? It can be anything.
Yes.
It can be anything. Although it depends on the EMF E, V will be actually equal to EMF E, but EMF could be anything. So ultimately, V could be anything. This is the something about the open circuit. Okay, so open circuit guarantees about I is also always equals to zero. Is this clear to you people?
Yes, sir.
Yes.
The second is short circuit. Short circuit, what do we mean by the short circuit? Short circuit, we mean that this is a voltage source and we had actually connected the batteries like this with a single wire, with a single wire. So what will be the condition for the, what can we always be sure about for short circuit?
The current will flow.
What can we say? That, no, not that.
It
What
will
can we say
establish
about the,
potential difference.
it will establish a potential. We can always say that potential of point A is same as potential of point B. Yes or no?
Oh yeah.
Because they are actually the same points. So potential of A is same as potential of B. So what we can say that here terminal voltage will be zero. Okay. What we can say? Terminal voltage will be actually zero. Okay. Is this clear to you?
Yes, sir.
Okay. So this is the condition. And what will be the current? Current we don't know about. But one thing we can say that I will be actually maximum here. I will be actually here the maximum. Correct. If we connect any other resistor here, it will ultimately get reduced one. Okay, so you cannot reduce the R any more than this, so it will be this. Is this clear to you people?
Yes, sir.
Okay, now one more thing is the case, that is the charging of the battery.
So the previous case, could you just explain one more time?
See, what is happening here? What is the potential terminal potential between VA and VB? What is the potential difference between VA and VB?
Zero.
It is zero. So that is, I had said that the terminal potential will always be zero. I will be maximum in the short circuit time. That is why what happens in our case for the whenever the fault happens,
Sir, if
actually
terminal
very
voltage
high current used to.
is zero, will the current flow through that branch? Or no?
Yes, actually the current will flow. Okay, so that is see, I don't want to go into that particular thing. I can ask a lot of things over this particular thing again. Okay, tell me one thing, that whenever there is a wire, whenever
Yes.
there is a wire, so what we say, this point and this point is same actually. है ना? But we used to always, whenever we draw a circuit, we use some wires always. है ना? Apart from the resistors, we always use some wires as well. Okay, so if this point and this point is the same one, so its potential is always zero. If potential is zero, so what can we say? That no current will flow in that particular wire. Let's say
Hmm.
if this is the circuit that we had drawn, so if we select the 2 points here, they are joined together. So the potential difference between those two is zero. So if that is zero, so there should be no current in it. है ना? But ultimately the current passes. The reason behind that is
Yes.
because, see, what is I is equals to V by R. Yes or no?
Yeah. Yes, sir.
If V is tending to zero, see, actually you can never say that V is zero. V is tending to zero. So you should also remember about that R is also tending to zero here, na?
Yeah.
So it is something limiting case happens and current passes here. Okay.
Okay.
So
Yes, sir.
don't get into the mathematics here. Just Okay, so I will be maximum in this case for the short circuit time. Now the charging of a battery, we are talking about the charging of a battery. See, always you had seen that whenever we use a battery like this, the current passes like this. Yes or no?
Yes.
So charging of a battery, what is going to happen? That this time, if this is EMF E and this is R, so the current will pass this time like this. So this is called the charging of a battery. Is this clear to you people?
Yes, sir.
The current goes into positive terminal. So this is VA and this is VB. Which of the terminal is at higher potential, VA or VB?
VA.
Yeah.
VA is higher one. Okay. Current always moves from higher potential to lower potential. So what I can say over here, that what I can say, okay, just apply the Ohm's Kirchhoff's law again here. So what we'll get? VA minus of E minus
Yeah.
of I into R is equals to VB. Yes or no?
Yes.
Yes.
Then again, VA minus VB will become E minus of I into R. Oh, sorry, E plus of I into R.
Plus.
Plus.
Yes or no?
Yes, sir.
And
Yes, sir.
what we'll get? VA minus VB is actually the terminal potential. VA minus VB is actually again the terminal potential. So that is V. So this V is equals to E plus I into R. Okay. So this V is
Yes.
actually equals to E plus I into R. So can you see that the terminal potential is greater than E? In E, you need to add something in order to get the V terminal potential. So what we can see over here, that the charging happens whenever the terminal potential is greater than the EMF of the battery. Okay, the charging of the battery happens only when terminal potential is greater than the EMF of battery. Is this clear to you people?
Yes, sir.
The charging will always happen that whenever the the terminal potential will be greater than that one. Okay, is this clear to you people?
Yes.
Okay, let's do a numerical over this particular case. Uh, let me see. Let Do I have any? This one. I think this one will be nice. Okay, so take a easy question so that we should understand only the charging. A battery is connected. 500 ohm is here. Yes, and a resistance R of 100 ohm is here. It is connected like this, and a 2 volt is connected like this. Okay, and this is 12 volt. Yes, this is 12 volt. This is 500 ohm. This is 100 ohm. Okay. Find out the currents in every branch. Find out this current here and this current in the second branch also. Okay, first of all, we'll mark the currents over here. है ना? Mark the current in every branch. Okay, let us mark the same current, every one of us. So how you people want to mark the current first of all?
That I1 goes from 12 volt of
Okay,
battery.
so I1 is leaving like this. Then it will
Then
come at this point. It will get distributed.
yeah, then I2, then
I2 in
another
which
current,
one? 100 ohm or the 2 volt one?
2 volt,
2 volt one. I2 is going. And
and the
then in
other
this branch?
I1 minus I2.
Yes, I1 minus I2, not I3. Okay.
Yeah.
So I1 minus I2 will go in this branch. Now apply the KCL, KVL. Okay, again the charging will not happen here, I think. Yes, charging will not happen.
So the I2 doesn't have any resistance.
I2 does not have any. No, there is no resistances. This question also charging is not going to happen. Let me see that if there is any other.
No, no.
Now do it fast. Okay. Apply in the first loop and apply in the second loop. What is the equation that we are getting in the first loop? Starting from any point. Mark any point over here. Let me mark this point as A. I hope you people had also marked this point only.
Yes.
Yeah.
Okay. So just start from A. Yes, Rajan, tell me that the equation for the first loop.
Plus 12 V.
Plus VA plus 12.
Okay. So let's just tell the final one, like sum up, like everything.
The first loop equation.
Yeah, that's what. Then I got like minus
VA
500.
plus 12 minus of
Yeah,
I1 into 500
then
and
I
then
took it as like minus
minus
I1
of
100. Yeah, minus
100
I1
into
100.
I1 minus I2.
Yeah, like that.
Yes. Okay. And we'll reach to the same potential VA. Yes or no?
Yes, sir.
Then VA will get cancelled. The coefficient of I1 will be, I think, 600 with minus sign.
Yeah, 600 minus
Yes.
600. Yeah,
And the coefficient of I2 will be plus of 100 I2.
100. Yes,
Yeah.
sir.
And we'll get the plus 12 also in this side only. It will be 0. So what can I do here? That I1, we are just keeping the things a little positive. So I1 will be this, and with plus sign, minus of 100 I2, and it will be equal to 12. Yes or no? Have I
Yes,
done
sir.
the thing correct?
Yes.
Yeah.
Yes. What next?
Second loop.
Yes, second
Sir.
loop. Then what is going to happen in the second loop? Yes, I'll tell me
Sir,
this time
if we
what will be the
start
equation
from
here. This which point?
bottom right, below the battery. So final equation will be 100 I1 minus 100 I2 is equal to 2.
No, tell me the loop equation, whatever we'll write here. Which in which way you want to move, like this or this one,
Anti-clockwise.
in anti-clockwise. Okay, so start it VB, then
VB plus 2
plus 2,
minus 100 into I1 minus I2.
I1 minus I2, and
Yeah,
we'll get
equal
reach
to
to the
VB.
same potential VB. Okay, so VB will get again cancelled out, and what we'll get, the coefficient of 100 will be I think the 100 times I think minus of 100 I1 and
Yes,
plus of 100
plus
I2
100.
and plus of 2 will be equals to 0. So what will be the thing here? That 100 I1 minus of 100 I2 will be equal to 2. Okay.
Yes.
So what next I can do? I1 minus of I2 will be equals to 2 by 100. That is equals to 1 by 50. Okay. Then just substitute the things. Replace the, I think I1 is replacing easy. I2 plus 1 by 50. replace it in the above equation. That is 600 times of I1. I1 is I2 plus 1 by 50 and minus 100 times of I2. Let it be like this and equals to 12. So what we'll get? 500 times of I2, and if we'll just multiply it, we'll get plus of 12 and it equals to 0. Is it becoming like this?
Yes. Uh,
Wait. 600 I2 minus 100 I2, that is 500 I2. And this 5 ones are 5, 5 twos are 10, that is plus of 12 and is equals to 12. Yes or no?
Yeah.
So are we getting the I2 equals to 0?
Yeah. 0.
yeah.
We are getting the I2 to be equals to 0.
0.
If we are getting the I2 to be equals to 0, why so we are getting the I2 to be 0? What will be the I1 then? I1 will be 12 by
I want
600.
12
yeah,
by
12 by
600.
600.
Okay, that's a very nice question. Okay, 12 by 600 into 100. Yes. Now see. Previously we were discussing something about this and something arrived here. Okay, so this I2 is 0, and then what is the I1 here? I1 is
12 by
actually,
600.
if we'll just replace it in the above equation, you will get it to be 1 by 50. Is this clear to you people?
Yes.
Okay, now see this amazing result. Why we are getting the I2 to be equals to 0? We are getting the I2 to be equal to 0 because the potential drop across these two terminal is also 2 volt. The potential drop across these two terminal. Now, if you ask me to redraw this circuit, what it will become?
Yeah.
It will become like this. Okay,
Mm.
it's 12 volt, it's 500 ohm, and it's 100 ohm. Yes or no? What we can see that the current in this branch is 0 ampere. Or if it's a 0 ampere, so we can't mark the direction, whatever the direction you choose, it doesn't matter here. But the terminal potential is actually the 0 over here. So, sorry, the terminal potential is actually the 2 volt. The I2 current will be 0. The reason behind that, because see, can you see this in this loop? If you apply the voltage divider, if you apply the voltage divider over here, so what you can see that among this loop, this 500 and 100 will become in series, and 12 volt is getting divided into 500 plus 100 and multiply it with the 100. What you will get? You will get the result to be 2 volt.
Yes.
Yes or no? So that is why the current given by this 2 volt battery is actually the 0. Okay, but still you can see that the potential drop across these two terminals is still the 2 volt. That was the mandatory condition by an ideal voltage source, that it will always establish a same potential difference across its two ends. Is this clear to you people?
Yes, sir.
So this was one of the good question that we had seen over here, that this time this battery is being connected, but still the potential difference is actually it is providing us the zero current. I mean to say this. Okay, it is providing us the zero current over here. Okay, is this clear to you people?
Yes, sir.
Okay, now moving on to one other thing, that is, see, okay, let us combination of cells. Okay, let us do one thing. Let us take, okay, V1, V2, V3, V4, V5, R1, R2, R3, R5, R6, R7, and R8. Now see, can you people see that only one current is going to pass through this loop? That is the
Yeah.
I current. Okay,
Yes.
Yes,
so
sir.
apply the KVL over here, starting from this A point. Okay, if we'll apply the KVL from here, what we'll get? VA minus of I into R8,
IR3
then
plus V5
Then it will
plus
be
of
5 plus,
V5, then
and
minus IR1
minus of R. Yeah. And minus
then
I R2. Then minus V4. Then minus I R3. Then I R4. Then plus V3. Then minus I R5. Then minus I R6. Then negative V2. Then positive V1. Minus
is equals to VA,
VA.
same potential. Yes or no? Okay,
Yes.
now VA will get cancelled out. Now plug the things and let's see that what the result is going to be. Okay, uh,
Hmm.
let us say that let us do one thing, that club the I here. If we'll club the minus of I here, so what we'll get? R8 plus of R1 plus of R2 and plus of
R3
R3 plus of R4, R5, R6, anything left?
percent
R7.
7
R7.
Okay, and club this V all. Okay, so what we'll get? Plus of V5 and okay, plus of V5 and minus of V4, and
Plus
then
of
what
V3.
is there? Plus of
plus
V3 plus
V3
V3.
V3 and then
Minus V2.
minus of V2 and plus of V1
V1.
is equals to 0. Okay, if you want to find out this I current, what it will become? It will become this potential, that is one this V1 minus of V2 plus of V3 minus of V4 and plus of V5 whole divided by R1 plus R2. Can I write it like this? Ri
Yeah.
I from
Multiple
1 to 8.
conjugation.
Can I
so
write
that
it
will be
like
equal
this?
to minus I, right?
Not minus I, that will be equal to plus
Because
I. See it
we're
carefully. See it carefully. First of all, I'm transporting this whole thing on the RHS and dividing it by the same thing.
more than
If
dividing
I
it, yes.
transport it to the RHS now, so I'll get this.
Yeah.
Okay. So see, can we see this? That here the all the voltages are in series actually, because the same current is passing through all the resistors. Yes or no?
Yes.
Yes.
Same current is passing through all the resistors. So actually, whenever the voltages are in series, so you can use this thing, that what is this? This is actually becoming the V equivalent here, VEQ. So previously we had seen the combination of the resistors. Now we are seeing the combination of the cells. So what we can see over here, that see, if you want to draw the cell like this, okay, one thing we are sure about, that all the resistors are in series.
Yes, sir.
Yes.
So let me write it as R equivalent. Now see, what we want is we want to draw the equivalent of it. So if we are treating the things like this, so all the current, so this will transport the current like this. So whichever the battery is providing us the current like this from its positive terminal, take it as positive. Whichever the battery is in this manner, I mean, if I draw like this, so I'll take this to be positive. So what I'll get here, that V5 and this is the opposite of 1, minus of V4. This is plus of V3. This is again the opposite of this, minus of V2. And this is again the plus of
Plus V1.
V1. Okay. If I and then again connect the things like this. Just do this. Okay. So this is actually the V equivalent that I had got over here. What I mean to say over here, that if the cells are joined somewhat like this, so instead of across this AB point, you can join a single cell. Let me mark it as V1, not V1, let me mark it as E1, E2, EMF, E3, E4, E5. So if I want to draw a single voltage source like this, so as I can see that all the cells here are in series. All the cells are here in series. So if I want to do it like this, so whoever the battery is in this configuration, I'll take that thing to be in positive manner. So what do I mean from this? This I will write E1. This is same as the I treat this configuration to be the positive one. So plus of E2. This is the opposite of the one. Minus of E3. This is again the same as, so plus of E4, and this will be same as plus of E5. Is this clear to you people? And these are the 2 points, that is A and B. Is this clear to you people?
Yes, sir.
Suppose instead of taking this over here, if I would have taken this to be in this manner, I think the opposite of the one, then whoever the battery is in this configuration, I take that to be positive and the rest to be negative. So this time, can you people see this E1 will become minus of E1? Yes
sir.
or no?
Yes.
And this E2 will become plus of E2. This E3, no, not E2 E2 will
No,
also be
no.
negative. E2 will also be negative.
Okay.
E3 will be positive. Then minus of E4 or E3. Okay, minus of E4, and this E5 will again be in minus sign. Can you people see this?
Yes, sir.
And it is nothing. If you take the minus sign here common, E1 plus of E2, and what is there? Minus of E3 plus of E4 and plus of E5. You'll get this result. And this is nothing but the lower one result which you had got. If you are marking this to be E equivalent, so you'll mark this to be minus of E equivalent. Yes or no? So both the results are actually the same. Okay. Why I'm saying this? Suppose if I'm taking a battery like this to be 2 volt, and I'm saying that I had not taken this battery, I had taken this battery of minus of 2 volt. Both the things are actually the same.
Yeah.
Both the things are actually the same thing. If I'll invert this, what I'll get? I'll get this to be 2. Is this clear to you people?
Yes, sir.
Yes, sir.
So this is something that you should know about, that we can actually in series combination you can sum the all the EMFs. Is this clear to you people?
Yes.
Okay. And if there are some internal resistances as well, if there are some internal resistances as well. Okay, so for that, let me okay, so this is E1, this is E2, this is E3, and this is R1, this is R2, and this is R3. These are the 3 cells we had connected in series across the potential A and B. If I want to take a equivalent of this, what I'll do? First of all, I'll choose the battery, that whether I want to draw it like this or I want to draw it like, I can draw it in any way. In both the ways, I'll get the same answers. Okay, if I'll draw it in this way, so I'll replace it with this and a equivalent R equivalent. internal resistance. Okay, and this is E equivalent. So this E equivalent will be, yes, Regent, tell
Yeah,
me that what
minus,
will be this E equivalent be equal to?
yeah, minus E1, then plus E2, then
Minus of
minus,
E1.
yeah. Oh no,
You
yeah,
ha
that,
you have to take all the cells who are in which are in this configuration to be positive.
oh,
Okay, so this is plus of E1 now. This
so
figure and this figure is same.
what, the current is going from left to right or right to left?
Current doesn't matter here.
Oh.
Current doesn't matter here.
Oh, for
If you
that,
are
yeah, yeah, E1, E1, yeah, E1, then minus E2, then plus E3.
minus
Yeah,
of E2 and plus of E3,
yeah.
okay, and R equivalent will be the sum of all these, that is
Sum of,
R1 plus R2 plus R3. Is this clear to you people?
yes, sir.
If I would have taken the this cell to be in another way, that is in this way, okay, so yes, I will tell me that what will be the equivalent this time.
Minus E1 plus E2 minus E3. So it's
Minus E1 plus of E2 and uh, minus of
minus of
E3.
E3. This is
Okay,
minus
so
equal.
whichever are in this configuration, I have to take that particular thing to be in positive. The rest all of them will become negative. Okay, so you have to sum here also. You are in the series configuration, you are doing the sum of them, but properly, okay, with signs. So you have to take care about this. Okay, is this clear to you people?
Yes.
Okay, and this is called the series combination of the cell. This was the case one, that is the series combination. Okay, now again, the second thing will be the cells will be joined in the
Parallel.
parallel configuration. Okay, so let us do the parallel configuration as well. Let us draw the circuit for the parallel combination. Okay, so in parallel configuration, the circuit will look somewhat like this. Again, you have to draw the circuit similarly as we had done in the resistors, but the only thing will be that you have to take the cells and what else will be there, that you have to take the internal resistances as well here. Okay, is this clear to you people? Okay, so just draw the circuit over here first of all. Let us take that this is the cell that we are drawing. Let us do it for the two cells only, and then we'll generalize the result for the other ones. Okay, so this is the circuit that is being joined across AB. Let it be E1, R1, let it be E2, R2. Okay, what our aim is again to replace it with a circuit like this that will be E equivalent and this will be R equivalent. Okay, is this clear to you people?
Yes, sir.
Okay, now let us see that the terminal voltage across the first cell, the terminal voltage across the first cell is the same as the terminal voltage across the second cell as also. Yes or no?
Yes.
Yes, sir.
Okay, so let us first of all choose a direction of the current. Okay, so let us say that this is the direction of the current coming on I1, and let us choose this direction also to be I2. So if we apply the KCL over this node A, what will be the equation for I1 and I2? The incoming current will be equal to the outgoing current. Yes or no?
Yeah.
Yes.
Yes, sir.
So KCL at A. So what is the incoming current?
I1 plus I2.
I1 plus I2. What is the I2 outgoing current?
I
That is zero.
I
0.
Okay, that is zero. No current is going outside. So what will be the result actually? Actually, one of this I2 will become negative. One of them will become negative. Okay. So you will see that one of the I2 is becoming negative and the things will become like this. Okay, is this clear to you people?
yes.
Okay, now what next we are going to do? that if we apply the KVL in the first cell, what we'll get? If we apply the KVL in the first cell, let us say that which of the terminal will be at higher potential, VA or VB? Which of them will be at higher potential?
VV.
VB will be higher potential. So VB will be higher and VA will be lesser actually. So actually VB minus VA, we are saying it to be V. Okay, so apply it over here. What we'll get, starting it from any point. Okay, let us start this time with VB point. So VB and then minus of I1 into R1 and then plus of EMF E1 will reach to the point VA. Yes or no?
Yes.
Okay, so that means E1 minus of I1 into R1 is equals to VA minus of VB. Yes or no? Yes or no?
Yes.
Yes, sir.
Okay, now see, we want to replace this with a equivalent of this. Yes or no?
Yeah.
Yeah.
We want to replace this with the equivalent of this particular thing. If we want to replace this with the equivalent of this particular thing, so in this circuit, which is at higher potential, VA or VB?
VB. VB.
Here.
So so there it's
VA.
Okay, here also what you can say that actually na, we instead of these two cells we should take three. That's more convenient, because if we are taking only two, so it is becoming quite like a series combination. Yes or no?
Yeah.
Is it not becoming like a series combination?
Yes.
So
Yes.
instead of two, if we take three, I had thought that if we take two, so that will become easy for us. But I think that if we'll take three, that will become easy for us. Because if we are talking about two, so this is actually giving us the series combination one. Yes or no?
Yes.
Yes.
Can you people see this, that this is becoming a series combination here? So instead of two, mark it as P. Although doing it for two or three doesn't matter, because you will see that we can derive the things from one to another one also. Okay. Now see I1, I2, and let us
I3.
mark this current to be I3. Okay. Now again, you people will ask the same thing. So let me mark this to be I3 only. And this time what I can say that I1 plus I2 plus I3 will be actually equal to 0. And if we'll mark the I1, so we'll get the results to be like this. EMF will be for the first one, it will be like this. And what is this actually equal to? E1 minus of I1 into R1, and this is actually equal to V. Okay, VA minus VB. We are treating that, or we should take it as minus of V na, because VB is at higher potential. Yes or no? VB is at higher potential.
Yes.
Okay, and similar kind of thing, if we'll apply the thing for the second one, so what we'll get? VB minus of I2 into R2 plus of E2 will be equal to VA. Yes or no? And the same thing, that is E2 will be equal to, what will be this? E2 will be equal to, E2 will be equal to, that is minus of I2 R2, and this is again VA minus VB. Okay, instead of writing it like this now, let me write it as VA minus VB only. Okay, and similarly for third one also, VB minus of I3 into R3 plus of E3 will be actually equal to VA, and the same thing, that is E3, okay, minus of
Yeah.
I3 into R3 is equals to VA minus VB. Okay,
Yes,
now
sir.
finding out the I1 from the first equation. Finding out the I1 from the first equation. What will I get? I1 to be equal to VA minus VB and plus of what I'll get VA minus VB minus of actually
minus
E1 and divided
upon.
by R1 and divided by R1. Yes or no?
Yes,
Yes.
sir.
The same thing I can get here also. I2 will be equal to VA minus VB divided by R2 and minus of, am I doing anything wrong? Yes. I think this will be with the negative sign
Negative.
and this will be the positive sign. Yes or no?
Yes,
Yes,
sir.
sir.
So this will be the negative sign and this will be E2 by R2. Okay. And similarly, you can find the I3 also. It will be minus of VA minus VB and divided by R3 and plus of E3 by R3. Yes or no?
Yes, sir.
Now, what is the thing that if you sum all these three, if you'll sum all these three, what we will get? If we'll sum these three, we'll get the answer to be 0. Yes or no? From the first equation.
Yes, yes.
So just sum these three. What we'll get that I think you can see this that VA minus VB with a negative sign will remain here. 1 by R1 plus 1 by R2 plus 1 by R3 and it will be equal to E1 by R1. Should I do it a little fast? I can
Yeah.
actually, I'll get this result. Can you people see this? The sum will be 0. If we'll transport the VA minus VB on the another side, I'll get this result.
Yes, sir.
Yes, sir.
Can you people see this or I should do it?
No, it's fine.
It's fine. Okay. Now tell me that what this VA minus VB is. E1 by R1 plus E2 by R2 plus E3 by R3 and whole divided by 1 by R1 plus 1 by R2 plus 1 by R3. Yes or no?
Yes, sir.
Yes, sir.
And what is this? This is actually the terminal potential.
Yeah.
So what can I say? That this is actually nothing but E equivalent. That is E1 by R1 plus E2 by R2 plus E3 by R3 and whole divided by 1 by R1 plus 1 by R2 plus 1 by R3. Yes or no?
Yes.
Yes or no? So this
Yes,
is
sir.
actually the E equivalent in the parallel combination. In parallel combination, it comes out to be this. And what the R equivalent will become? R equivalent will be nothing but 1 by R1 plus 1 by R2 plus 1 by R3 also as well. Okay. Is this clear to you people? That R equivalent, they are in actually the parallel one you can consider, and that will become 1 by R1 plus 1 by R2 plus 1 by R3. So our ultimate goal is not to go into this, just to remember this, that whenever the circuits will be given to you like this, see, like the way we had seen this proof, although this proof will not help you while solving the questions a lot, you have to remember this thing in order to, okay, just this is the final conclusion that I'm giving to you. Let's say that this is 2 ohm, this is 1 ohm, and this is 3 ohm. Okay, and let's say that this is 2 volt, this is 3 volt, and this is 5 volt. Okay, let us consider this. Now, what we are going to do, across this AB point, we are going to connect a single one. We are going to connect a single resistor and a internal resistor like this across this AB point. This is the E equivalent and this is the R equivalent. What this E equivalent will be? E equivalent will be actually equal to, see, if I had drawn this battery like this, you have to take all the configurations in this to be in positive. So that will become 2 by E1 by R1, 2 by 2 plus 3 by 1 and minus of 5 by 3. Is this clear to you people? And
Yes,
divided
sir.
Yes.
by 1 by 2 plus 1 by 1 plus 1 by 3. The R always are in positive, so not need to do anything in that. Is this clear to you people?
Yes.
Yes, sir.
Now solve the equations and you will get the answers. Now, and R equivalent, this R equivalent will be 1 by 2, oh, not this R equivalent, this is 1 by R equivalent, 1 by 2 plus 1 by 1 plus 1 by 3. Okay, is this clear to you people?
Yes.
Yes, sir.
This is something that you should always remember about, that this is the combination of the cells. Whenever the circuit comes like this, where the cells are joined in the parallel combination, so you need to apply this particular concept there, and you can actually, whenever required here, although I'm giving you uh, the hint that uh, you will get a very less chance to do this. Okay, and I'll even suggest you that do it whenever you feel that the question is meant for this particular concept. Okay, otherwise apply the KCL and KVL. Although you can see while finding out this derivation, we are actually using the KCL and KVL. So even whatever the question is being asked here, na, it doesn't matter. Although if you remember, do you people remember that we had solved this kind of question? We had solved this kind of question in one of our class. So this is actually the parallel combination of the two cells. If you people want it, you would have replaced this particular combination with its equivalent, and you can calculate the rest of the things, the I current and all other things in here. Okay, is this clear to people?
Yes.
But
Yes,
I recommend you to not to apply this formula a lot, because this formula uh, simplifies the thing, but it doesn't give us a big picture about the question. See, while after replacing this thing here in this particular configuration, now you people don't know about that what the current here is, what the current here in this branch is, what the current here is in this branch. Okay, you had replaced it definitely. So you should apply this particular thing whenever this particular configuration is connected with some other particular stuff, and you don't have to do anything with this particular thing. So in this place you can replace this and can analyze the circuit for the rest of the circuit. Okay,
yes,
because once you replace this particular thing, this particular combination of these three cells into this one, now you people don't know that what is the current in this branch, whatever the current is in this branch, whatever the current is in this branch, we don't know about it. So it actually doesn't give us a lot of information. So that is why I told you that whenever this particular configuration is connected with some other stuff, for example, there is some, so in this place you can replace this, because you know that you don't require anything to do with this particular part of the circuit. So you can replace this one and can solve out for the rest of the circuit. Okay.
Yes.
So this is particular thing that I was going to tell you. So you must remember about this thing. Is this clear to you people? Should we move on to the next thing?
yes,
Yes, sir.
Okay. I think that only one thing, that is power, is being left here. Okay. Just a second. Give me a second. Eardrops. My eardrops are getting discharged, so let me connect it. Okay, my voice will get disconnected for a second. So yes, now is able to you people.
Yes, sir.
yes,
So it always get discharged at the same time, because a previous class used to happen here. So
Yeah.
it already had worked for 1.5 hours. So it is working now for the second time. Okay, so this was the thing that I was going to tell you. Now only one thing, that is the power, is being left here. So apart from the power, I'll tell you some of the small things. Now see, the chapter is almost over. Okay, only the power is being left, which we'll cover in the next session. Power and the maximum power transportation theorem. Okay, MPT. That we'll study in the next class. For the time being, I'll tell you some of the rest of the small part of this particular thing, this particular chapter. Okay, one is there, that is the uh, temperature dependency of the resistance. C of resistance. Okay, so what do you people think that uh, do the resistance changes on changing the temperature? Sorry.
Yes, certainly right.
Yeah, why so? Why yes and why no? Yes, why do people think that the temperature resistance will change and resistance will not change? See, so what we used to see that on the temperature, the resistance depends. Why so? The reason is that it is because of the internal configuration of the resistors. Resistors are made up of some material. Okay, resistors are made up of some materials. So what is the resistance? Resistance is actually the it is felt by the electrons when it move in the circuit. So whenever the temperature changes, the movement of the electrons gets changed. Okay, and what we can say, it depends on the material. Okay, that on a particular temperature, whatever will be the resistance, it depends over the material as well. Okay, so what we can say, that the temperature decides the value of the resistance also. Okay, so write a point over here that for metallic conductors, if temperature rises, resistance also increases. Okay, so whenever the temperature rises, the resistance also increases. The reason behind that is, see, whenever there is a metallic conductor, so there are already a lot of the electrons present inside it. So a lot of charges are already present here. So whenever the temperature rises, the vibration in the metal starts. Temperature starts moving randomly. Okay, so as the randomness increases, I'd always told you about one thing, that randomness always leads to zero. If you will it's very natural thing that if
Yeah.
we'll try to study everything, we'll not be able to study anything. Okay, so
Mm.
that is the thing, that the randomness leads to zero. Okay, so that is why as the random vibrations increases in the metal, the conductivity will decrease. What we can say, that
Yes.
the electron will not start moving in the one direction. As a result, the resistance increases. Okay, while this is for the conductors, that is the case that I was talking about right now. Okay, for insulators or the semiconductors, insulator we already know, we had discussed, we used to discuss something about this in chapter 1, uh, but you already have uh, estimation of that particular thing, that the insulators are the one which do not allow the electrons to move across it.
Electrons.
Okay, and semiconductor is the one that we'll study here in the in the further course. So insulator and the semiconductors are the one that when the temperature rises, the resistance decreases. Okay, why so?
Yeah.
Because they do not have the abundance of the electrons. They do not have the sufficient amount of electron. As the temperature increases, the bonds break and the electrons are produced. So the charges are increased. So as a result, for insulator, A, okay, for insulator, if temperature, for insulator or semiconductor, you can write. If temperature increases, resistance decreases. Okay, resistance decreases. Is this clear to you people?
Yes, sir.
Okay. Now, what is the mathematical relation that is being are going to be used here? That is that at some temperature, actually, I'll say. Okay, so let us say that it is at the 0 degree Celsius. At 0 degree Celsius, if we consider the resistance, yes, resistance to be equal to R naught. Okay, and at some temperature T degree Celsius. Okay, T degree Celsius, resistance equals to R T. Okay, let me mark it with RT. Okay, so if this is the thing, then we used to define the temperature coefficient over here. Coefficient of resistance. That is the alpha. We used to define this alpha as change in resistance whole divided by, that we say, original. Okay, let me write the word here. Original resistance into delta T. That is the change in the temperature. That is the change in the temperature. So what you can say about the alpha for conductors? What you can say about the conductor, that alpha is whether alpha should be positive or the negative?
Negative.
See, always remember this, that change is always final minus initial. R final minus R
It's
initial.
only positive.
So for the conductors, what you can say, that alpha will be positive. The reason behind that, see, original resistance will be somewhat positive value. Okay, so this is somewhat positive. If we increase the temperature, so delta T will be positive again, because change is always the final minus initial. So it will be positive. Yes or no?
Yes. Yes.
And for the conductors, if we increase the temperature, which of the will be increase, which of will be higher, RF or RI?
RF.
RF will be higher, because as we had increased the temperature, the resistance has been increased. So this term ultimately will
Yes.
become positive. So alpha will be positive. Now for the what we can say, conduct insulator or the semiconductor. For insulator and semiconductor, what alpha will be? Positive or the negative?
Negative.
It will be somewhat negative. You can analyze the thing. If the temperature increases, the upper numerator will become negative and the resistance will become somewhat like this. Okay, is this clear to you people?
Yes, sir.
Okay, so remember this. Now moving on to the next thing, that what I can say here, that alpha is what? RT minus of R naught divided by R naught into change in temperature. Let me mark it with delta T. Is this expression I had written correctly?
Yes.
Uh, just transport this denominator over the another side and find out the RT here. So RT will actually become R naught into 1 plus alpha times of delta T. Can you people see this?
Yeah.
Try to analyze the thing, that uh, transport this on the another side, shift the R naught on the another side, you'll get the thing. Yes or no? Is this clear to people?
Yes. Yes, sir.
Okay, so that is the something that we should know about. Okay, and SI unit of alpha is what will be the SI unit of alpha?
Uh,
Uh,
resistance by temperature.
Resistance by temperature. Don't you think that this whole numerator is a ohm?
So yeah, that's a ohm.
The denominator is also ohm and degree Celsius.
Degrees.
Or
Yes.
SI unit, we should say Kelvin.
Kelvin.
Okay, so
Yeah.
SI unit will be Kelvin inverse. Okay, and CGS unit actually. CGS is, what is the CGS unit? What is CGS stands for?
Centimeter, second.
Yes, it will be
So
degree Celsius.
degrees Celsius.
Okay, is this clear to people?
Yes.
And from the insulator, what I mean, the materials like germanium and silicon, okay, that are actually the semiconductor one. Okay, semiconductor, I mean silicon, germanium, okay, germanium. So these are something that you should know about, and this is the relationship of RT and R1. Is this clear to people?
Yes.
Yes, sir.
Okay, so this is something that you should know about, and this was all about this thing. Okay, one more thing that I can write over here, although people used to see that via a question, but you can see this that the similar thing you can write it for the resistance rho t also, resistivity also. Rho t will be equals to rho naught into 1 plus alpha times delta. Okay, replace the RT by rho into L by A on both the sides. You will see that L by A will get cancelled out and you get this relation. Is this clear to you people?
Yes.
Yes, sir.
Okay, so this is something that you should know about, and that's all about this thing, and that's all about the today's class. One more thing, okay, tell me that if we change the temperature from 25 Kelvin, uh, let me mark it as, okay, 25 Kelvin to 250 Kelvin. What is the change in temperature?
225.
225.
225. Okay. And if I change it from 25 degrees Celsius to 250 degrees Celsius, what will be the change in temperature?
225 degrees.
225 degrees Celsius.
225? Are you sure?
Yeah.
Okay. So that will be 225 only. Okay. Sometimes what people used to see that, okay, the change in temperature, what will be the unit here? And what will
Degrees
be the unit
Celsius.
here? In the first case, the unit will be Kelvin.
Yeah.
Kelvin.
Kelvin.
In
Kelvin.
the second case, it will be degree Celsius or the Kelvin.
Degrees Celsius.
Degrees Celsius.
Can it be Kelvin also?
Yeah, if we convert it.
You convert
It can be.
Kelvin.
If we convert it, okay. So don't require so conversion. It can be degree Celsius or it can be Kelvin also. In the above case also, it can be degree Celsius or Kelvin. The reason behind that, if you want to find it out, okay, you people are always saying that, already saying that it is in degree Celsius. So let me do it for the Kelvin. If you convert the 25 degrees Celsius into Kelvin, what you will do? 273 plus 25. Yes or no? And you will
Yeah.
subtract it from 250 plus 273. This is the final. This is the final one in Kelvin. So if you'll do so, you can see that still you will get the 225 in Kelvin. This time in Kelvin.
Yes.
Yes or no?
Yes, sir.
Yes.
So this is something that you should know about. That change in temperature doesn't depend whether you are taking the change in degree Celsius or the Kelvin. Whatever the change you are taking, it doesn't matter there. It will always be the perfect already. Okay, so although the SI unit is in Kelvin, so we should take it in Kelvin. But if the in question it is given in degree Celsius, sorry, if it is given in the degree Celsius, then also if you find out the change, you will get the same answer. Okay,
Yes, sir.
but remember this: if this is in Kelvin and this is in degree Celsius, then you need the conversion. Okay, if I say 25 Kelvin to 25 degrees Celsius, what is the change?
Uh,
So what is the
What
question?
is the change? 273, no?
273.
yeah, 273.
Whether in degree Celsius or in Kelvin, it doesn't matter. Okay, as I told you, that the change can be of any unit in degree Celsius or in Kelvin. Okay, so that's all about the today's class. If you people have any kind of doubts in the today's class, you may ask, or else we'll tomorrow end up the next chapter. Oh, sorry, this one chapter, and we'll try to even start the next chapter. That is the ray optics. We'll start. Okay,
Okay.
ray optics or the pre. I don't think that we should move backward. Okay, we should
Yes, sir.
start the ray optics so that we'll be able to understand the things. Okay, so tomorrow we'll end up this chapter. That's all about the today's class. If you have people have any kind of doubt, you're most welcome, or else you people can leave now.
So the sample paper are so good, right? Is it good? Like, how good do you think like sample paper are?
Sample paper of the CBSE. Yes, have you people seen your date sheets?
Yeah,
Yes, sir.
yes, sir.
The CBSE date sheet,
Yeah,
the final board
Yes.
examination.
yeah.
So I think the paper used to be same na for the foreign or in the India.
Yeah.
Yes or no?
Yes,
Or
it's almost the same.
is it different?
Also, it's the same.
It's the same na? So I think that's the you people have seen your date sheets also. Okay, so start preparing for a board examination. That's all about that. And I had not seen actually the sample paper till now. So that's all. Okay. So
Thanks.
No, sir. Did you solve the sample paper like when you were a student?
oh, acha, you are asking that whether
Yeah,
I had solved it or not. So I thought that you are asking about that the CBSE sample paper that have been released.
yeah.
Okay,
That is also yeah. Both questions. Like,
so I think that you must solve the sample papers. Sample papers are not given by the CBSE one, but by some good publications like Oswald publication is there. Okay, that are the good sample papers. So you people can solve that. But rather than solving the sample paper, I'll first recommend